Hello, welcome again. In our last video, we started hypothesis testing where we were looking at cases. If you have maybe a data set where you know already, maybe a sample that you're carrying, a research, you already know the population standard deviation. You can do something like we already have these examples in our last video where we can do maybe a one-sided t-test, or maybe something that we can use a z distribution, or maybe a t distribution. Um, that works well, if we know most of these things, but in real life, we might not, know them. We will only be able to estimate them. So that is why today we are going to be looking at different scenarios where we are going to be looking at if we have maybe we carry out an experiment, we are trying to compare the mean between maybe female and male in depending on how we collected our data. So today we are going to be using the popular Palmer penguin data set we have been using throughout some of the videos. So first thing first, we know that we have to first of all load that library. We can also view that data. If I run that view, we're going to see the different species. So today, the first test we are going to be running here, let me also run the string of penguins so that we see the different columns. We have species, island, the bill length, the bill depth, the flipper length, which is all of this is in millimeters, and so on. So today we are going to first of all start with a two-sided t-test. What I mean by two-sided t-test is actually, let me just bring this here. I posted note on this in our WhatsApp group. Please make sure you can go through. I think that should be week either week 6 or week 7. So it's like if I'm trying to compare the mean between two different species, like I did mention, we are going to be using to see whether there is, find out whether the flipper length differs between the male and female chin strap penguin. So the no hypothesis here, which is A0, is that there is actually no difference in between those means, meaning that it is the same. And then the alternative here is saying that there is a difference. Most of you, you are going to see this a lot, whether you're working as a data analyst, you're working as a data scientist, where you'll be doing a lot of hypothesis testing, because most of the product that you see in marketing these days, they do a lot of hypothesis testing to make sure that the product that you are going to release, is going to yield, it's going to benefit any organization that you're working for. Even on Facebook, you will see something like here, t-testing, whether you're testing different metrics, whether when you post something, Facebook, when they develop their algorithms, they have to actually test whether it's going to work, for whether they are doing marketing or whatsoever thing they are doing, where they will do a lot of t-testing, which in most of the times they call it A/B testing. A/B testing is actually based on hypothesis testing. As we go ahead, we are going to see with real world data set, we do a lot of, we might not have the assumptions because before we carry out a t-test following the notes I posted, you have to make sure that the assumptions, like the normality assumptions, hold. Like you have to do some QQ plot, maybe do some histogram to actually make sure that that data is symmetric. But most of the real world cases, that data is not symmetric. But as we move on in this video, also in the notes I posted, you also notice that there are some methods which we call them the Bootstrap methods. Those are the cases that are used a lot in the industry today, because most of our data doesn't really come from an actual normal distribution, which when we move into machine learning, we are going to see why most of the times we might not want to use linear models a lot. We may want to use models that are non-linear, just so that we can find relationship between attribute, and then they are able to make some predictions accurately than using some linear models. Why? Because most of those linear models will still fall back to these normality assumptions that we are doing and in the notes that I post. So with that said, if we go back to going back to our two comparing those two means. So what we are trying to test here is a two-sided t-test. We are trying to test whether the flipper length for the sex, for those penguins species being equals to what the chin trap, whether there is a difference in between those means, as I did mention. If we come here, we see the difference. If we go to the sex here, we have what the sex here is male and female. So if I go back here, you do not have to go through like this first method that we're doing here, writing formulas and all the like. You won't be doing this most of the times because you won't do that manually. So that is why I decided to bring out something like a reward scenario where you'll be doing this, with the reward data set. I already, some of the videos, we saw how we can load data set in R and then do most of these things. So I will just do t.test. I'll pass that flipper length I want for the sex, and then the data I'm taking a subset of what penguins, and then this species is equals to what? Is equals to what? The cheese trap. You can use maybe the piping technique that we already have a video on that to solve the same problem rather than going through this. Or better say, you can pick out this subset data as something different, and then later on pass it as data here. So if I run this now, we see that most of the time we are interested in this p-value, and we know that the significance level that we use, most of statisticians use, is 5%. We see that this value is very lower than 5%. So we are going to reject that null hypothesis to say that there was no difference. And if we are rejecting that null hypothesis, our conclusion will be that what? Our conclusion will be that there is a difference in between the means of the flipper length for the female and the male chin trap penguins. So, and we also notice here that we have a confidence interval associated to E. Most of the confidence interval, will see them a lot because it actually tells you, it means a lot, how how the mean, where the mean actually falls between these two different species, that is male and female. Here we will have a negative. This negative, is simply meaning the way we are going to interpret it, it will be different if we were having positive values. A confidence interval of minus approximately minus 11 and minus 5.3 simply means that the average flipper length in females is somewhere between 5.3 and 11 millimeters shorter than in males. But if it was the other way around, the interpretation will be a little bit different if they were positive values. If they were positive values, we will say that for females is somewhere between 5.3 and 11.1 millimeters longer than in males, if it was actually that for the values were positive for the confidence interval. So another way we can do here is a one-sided t-test. One-sided t-test here is cases whether we are testing whether the mean for these female chin strap penguins, whether the mean for female is greater than that for the male, or the mean for the female is less than that for the male. We see that here we are passing this other function which says alternative inside the t.test. Here we did not do that because by default it assumed that it is a two-sided t-test. But to make sure that it is one-sided, whether you are testing whether the mean for those female, the flipper length is less than that for the male, you have to use what less than. If you are trying to test whether it's greater than, you are going to use greater than in the case of this alternative. If we run this also, we will see that we are interested in the p-value here. We see that p-value is far more, smaller than that 5%. We are going to reject the alternative, the null hypothesis to say that the mean for the male and female are equal, in favor of what? That the mean for the female chin strap penguins is less than that for the male. So you have to make sure that you know most of these interpretations. They are very, very important, especially in real world scenarios. Also, we are going to be having cases where we have a paired t-test. Paired t-tests, they might be common a lot for those of us that carry out experiments, especially that the data is dependent upon. For example, if we were going to run an experiment that you collect data in the morning and then you collect some within the day, or maybe you collect it in the evening, there will be some relationship in between that data. So that in that case, it will be more like a paired t-test. So in that case, the way you set up the hypothesis will be a little bit different. Here you will be saying that the alternative hypothesis here, if you look at the notes I did, look at those notes, you see that the alternative hypothesis here is that there is no effect um, in between those mean. Effect in the sense that if we are taking measurements on some subject before and after a treatment, in such situations, we are often interested in the effect, right? In the effect of the treatment that we are making. Where if we are looking at there is the alternative is that there is no effect, why the no is that the alternative is that there is an effect, why the no is that there is no effect. So most of the times you will find these scenarios, even some of the assignment that I gave you are going to find something like this. But in that assignment, you will notice that I'm asking you to first of all go through to test whether the normality assumption. So if we are going to test some normality assumption, we can first of all do maybe QQ plot, for example, and then we can do X data, and then we can pass our theta. Maybe we do we do some why is it? Let me just do, I don't know why histogram. We just do histogram of X data. Theta to actually make sure whether the data is coming from some symmetric distribution. Most of the times we want to plot this, we can see that this data is not symmetric, right? So it's like maybe like more left skewed. We can try also the is for X data, and then we pass after to actually we test most of these assumptions. So we see, yeah, even in this case it's not really symmetric as we might see. That is why most of the times we'll see as we move on we are going to be using bootstrapping, because most of our data in real world doesn't actually follow this assumption. So if we are using a t-test, the pair t-test here, we are going to do t.test. We pass in, we are looking whether the we are interested in running a two sample t-test to compare the two samples. So before and whether there is some effect after or before. So you see that paired here, we are taking it to be what? To be equals to true, because by default, the t.test takes that pair to be equals to what? False. So we must pass this pair is equals to true so that we will be able to test, run the pair t-test. So here we have this p-value. It is a little bit, small compared to that 5%. So if it is small, then we are going to reject that no hypothesis that there is no effect in favor of what? There is an effect for those different treatments. So so most of the times, as I did mention, if we are going to be following most of these assumptions in real world, the normality assumption, the data that we have these days is mostly skewed. We might not be able to have all these assumptions in place. So most of the times, and most companies, they prefer to go with what we call the bootstrap t-test, which is a popular method for computing p-values and confidence intervals that will resemble some permutation approach in the bootstrap. Bootstrapping simply means you are sampling from trying to pick samples from some population where the probability of randomly picking different samples is same, right? Like if I'm drawing this sample, the probability of picking another sample from that same population, it is same. But most of the times it is a random selection where there is some replacement drawn with replacement from that original sample that you are trying to pull from. So we will see this test is used a lot in real world. So before you run that test, you have to make sure that you see I commented out this. Make sure that you install this capital M, capital K, that's M key file library, and then make sure when you install it, you have to run it, and then same way that we normally run. So we are still going to do the same. We are trying to compare using that bootstrapping technique to compare whether the flipper length for those penguins, the different sexes for the species chin strap, there is some form of what difference in between those means or not. So let's run this. If I if I run this, you will see that we have a very low p-value, and then we see that the confidence interval here is pretty same like the other case. So most of the times we are doing this because we might not really have um, the normality assumptions being validated. So most of the times we are going to be using this test a lot in real world scenarios. That was it for this video. So keep following for more. If you have any question, always reach out. Thank you very much.